I'm going to begin giving a lecture for the first hour that is going to be completely unrelated to the rest of the course. It's going to be what I deem a hype lecture. It has a relationship to calculus, but it's non-examinable. Now, there's a bit of an unfortunate thing that we have with our format in that lectures are supposed to be 3 hours and 20 minutes long. So each lecture is supposed to be 3 regular lectures if this was offered in the course of a regular term. And that's a bit unfortunate because it's hard to concentrate for that long a period of time. I'm giving in each session essentially 3 lectures in a row. And I mean, the format requires it. So we're going to have to deal with what we get. And so I particularly want everyone to not get tired out in the hype lecture, because we're going to have to delve into some deeper material after this. Now, I'll say more about the structure of the course after the hype lecture. And again, the first hour of what I'm going to do is not in any way going to be examinable. And I hope it's just going to be an entertaining thing. So consider it an experience. This is a lecture that I've given 4 times, and I think it's a pretty good lecture. So the lecture is going to be on Greek geometry. And the notion of area. And I encourage everyone to stop at me and ask questions if any come up. I really like interaction and I really like student participation. So that would be great. Okay, let's see. How am I going to start this? Well, we've all heard about the ancient Greek civilization. We've all seen its art. We've heard about discoveries. We've heard about history. And we know that it's an amazing civilization that accomplished many things. One of the most notable things is that the Greeks were the first to do mathematics in a very peculiar, certain way. And in some sense, the history of mathematics begins with the Greeks. There's a lot you can say about Egyptian and Babylonian mathematics, which predates Greek mathematics, but there are many qualities of Greek mathematics that persist to present day, and many ideas from Greek mathematics that we can see in our daily mathematics. And you're going to see the ideas in this lecture come up in calculus as well. And you have to ask then, even with things like philosophy also, you can say that the originating point of philosophy is with the Greek civilization. So why was it that the Greeks had philosophy? Why did they have mathematics? What was special about their culture that enabled them to start so many fields? And there are several explanations for this. The one that I subscribe to is it's the peculiar thing about the way that Greek society was set up. They had this thing, it was called democracy. Well, it was a limited form of democracy. Not everyone had a say. Wealthy men had a say. And it was a very small group. But in some sense, among that privileged group, it was democratic, in the sense that every single person could sway the conversation. And what became a very prized skill was the skill of arguing. If you had a position, if you had a way that you wanted the world to be, then it was set up so that being persuasive in a public setting would have been something that would have let you got your way. Now, of course, there is absolutely no society that has ever existed in which the ability to persuade someone and the ability to speak effectively has not been a skill that has been valued. But in a certain sense, the novelty of Greek society and their democratic system was that it was held in an organized enough way, and people would meet regularly enough that arguing poorly you'd hear the same poor arguments time and time again, and then you'd eventually stop listening to them. It wasn't a matter of a 40, it was a matter of being persuasive. Now, there are several different ways that you could put this, but the ending point is that arguing has a special place in a democratic society. And so people began to study arguing, and they began to study what makes an argument true. And they began to study the foundations of what it means for something to be true. And so all for the sake of being able to argue better and for the sake of getting your way in by arguing your position. Right. And so you can say that's around 500 BC. You had a very built up theory of how to argue. And you also had a lot of other things built up. Arc, I am not delivering this one. Okay. So the story begins then with at a point where you have an established theory of how to argue. And you have an established theory of what it means for something to be true. And the Greeks have accomplished a lot at this point. So one of my favorite examples is this. It dates from the 6th century BC. This is an example in science. There was a village, and the village was at the base of a mountain. And the mountain, its width was around 1 kilometer. And they realized that they were in a position that was strategically poor. There was a river that was flowing around the mountain, and this was the town's only source of water. And they realized that a sieging army could cut off the river and cut off their water supply, and then they would fall in a siege under this. And so they decided that the way they get around this problem is that they would dig a tunnel through the mountain in order to have a pass at the lake that was on the other side. And this tunnel had to be 1 kilometer long. And the way that they dug the tunnel, and this is the fascinating part, is that they started digging from both sides simultaneously. It was a tunnel that was about, let's say, 2 or 3 meters in diameter. Both tunnels were dug 500 meters into the mountain, and then they met. And you can see, if you go there, this is called the Tunnel of Eupolino, that the two sections met within less than half a meter. And the way that they did this is there was a complex calculational method. There was a complex way to check it. They had calculational methods, they had engineering, and they were able to solve this problem. So this is the state already at the 6th century. And so you have a culture that has all of these accomplishments. And then comes along Parmenides. Parmenides, you can say that science and philosophy begins with him. If you were to draw a starting point, Parmenides is a good starting point to draw. And very little survives of Parmenides' work. His most famous poem is called On Nature. And of it, we only have maybe 25% of the fragmented lines. We have a lot of people that speak about the contents of this poem. And so what was Parmenides' poem On Nature about? In this poem, the narrator, he is at one point enraptured into the domain of a goddess. And what the goddess says to him is, I know the truth, I'm a goddess, I'm the goddess of wisdom. And what I'm going to show you is the way that things are. And I, as a goddess of wisdom, will not just tell you to accept what I say dogmatically, but I will in fact argue logically, and by a argument that's on its own merits with no sake of a 40 will be compelling enough to show you the true nature of things. And then she argues what the true nature of things are. And she begins with a very simple premises. The premises is along the lines of things that are, and things that are not, cannot be. And that's the starting premises. Sounds very reasonable. Then after several lines, the conclusion derived is that there is no such thing as different things. There is no such thing as change. The world is a single uniform thing that is unchanging and homogeneous. And from the sake of the argument, you can say that all of existence is essentially a closed homogeneous sphere that does not change, and that nothing that we see is real. And you may say, well, okay, that's a completely absurd conclusion. And why was this such an influential poem? And you look at what Parmenides does, and what Parmenides did is that he took several hundred years of Greek history and Greek society, all of the techniques that they had built to argue, all of the theory that they had crafted and that they had accepted. He started with premises which were acceptable, and then using precisely to form all of the methods of their time, he derived a conclusion that was completely absurd. And then you could look at this poem and you could say, well, that conclusion certainly isn't wrong. But then you look at the argument and say, where's the argument wrong? And to people at the time, they could not find a hole in this argument. The purpose of the poem was that it was written to derive this conclusion from arguments that were perfectly acceptable. And then people realized that their methods of arguing were wrong. So he derived a contradiction at the heart of all of the theory that you had on how to argue. And then people started getting really worried. Then they started re-examining their foundations. And this, in some ways, structures all of Greek science and mathematics. They are very fearful of having someone like Parmenides come along and completely destroy the foundation of everything they know. And so they're very careful, and they want to found everything in things which are certain. And they want it to be so that later it's not discovered that you can poke holes over and over again in an argument. And that leads to a very peculiar nature of what Greek mathematics looks like. You have things like lengths, you have things like areas. And then the question is, how do I found this in a way that I know what I mean by something like an area, or I know what I mean by something like a length or a shape? And so then we get to the history of what their foundations looked like. And this is a story about those foundations, and it's a story about a crisis that came up in those foundations and how that crisis was solved. So we should now look at what happens post-Parmenides. Well, I mean, this even predates Parmenides a bit, but following Parmenides is the point at which the foundations were starting to get written up. And so what I'm going to present to you is from Euclid. This actually comes at the end of the story that I'm about to tell. But it represents results that were known, let's say, 500 BC. So this is the clean final version of the foundations of Greek geometry, the foundations of what it means to talk about areas, lengths, shapes, etc. And so Euclid, the book, by the way, does anyone have any questions? Okay. So Euclid, the book, and again, this is the most polished, this is a clean way of talking about all of this, begins with several definitions. I'm just going to highlight some of them. And again, the definitions say what we're talking about. In some sense, they're opaque. It begins with the first definition: a point is that which has no part. Well, I guess we all know what a point is. A point is a point. I've drawn a point, but this has some area. I don't mean an area, I mean just a single point somewhere. Is this definition informative? Maybe, maybe not. You can argue both ways, but it's the starting points that we have. A line is a breadthless length. A figure is that which is contained by any boundary or boundaries. A circle is a plane figure contained by one such line, such that all straight lines falling upon it from one point equal one another. And that point is called the center of the circle. So these are just some definitions that I've highlighted. The key point is that for a circle has a center, and a circle is defined to be exactly all points that are at equal distance from a center. Well, not exactly equal distance. There's some lines don't have to be straight. All straight lines are specifically called straight lines, such that this encloses a figure, and there's some point in that figure, so that if you draw a straight line from the boundary to that point, any such straight line is equal. Now, what does it mean for two lines to be equal? I mean, this line is not literally this line. They're two different line segments. So what do we mean by that? And then we come to the common notions which clarify what really is meant by equality. And again, these sound all reasonable. Things which are equal to the same thing are also equal to one another. If equals are added to equals, the wholes are equal. If equals are subtracted from equals, the remainders are equal. Things which coincide with one another are equal. I should have that here. With one another, oh, no, things which coincide with one another equal one another. And then here's the very important thing, the whole is greater than the part. Now, you can also look at how the arguments occur. And then it's clear that from the arguments, let's see, there's a question in the chat. Oh, so there's a question of whether the notes will be on Blackboard. There are going to be notes on the course website. The notes will not cover this introductory lecture. They will cover everything else. And they can be found on the course website. I won't be posting things on Blackboard. And I've emailed you a link to the course website. Okay, continuing. So it becomes clear that what it means for two line segments to equal one another is really that they have equal lengths. A line segment is sort of a magnitude, and it's a magnitude of length. Then areas are magnitudes of areas. And then you have things that all line segments equal one another. For example, in the definition of a circle, this means that all line segments have the same length. So this is, and then I'm going to do some examples which give you a better notion of what these look like. Then finally, we begin with 5 postulates. Here are the axioms in a sense. Common notions look like axioms for equality, but the true axioms are these 5. And here's how I illustrate them. The first is to draw a straight line from any point to any other point. So axiom 1 says that if I have 2 points, then I can connect those points by a line. Axiom 2 says that if I have any line segment, any straight line right here, then what I'm able to do is I'm able to place a ruler to that straight line and I'm able to extend that line. Postulate 3 says that given any circle and any radius, given any point and any radius, you're able to construct a circle with that point at its center and with a given radius. And so these types of constructions are called compass and straight edge constructions. A compass is a tool for drawing circles of a given radius. You put it into your page and then you twirl it around and it draws a circle. And then a straight edge is just a ruler, except we are not calling it a ruler because it doesn't have markings on it. So you can't measure things. All that you can do is it's an unmarked ruler and you can't mark it. And then there are 4 more postulates, and these are postulates about angles and measurements of angles. That, for example, all right angles equal one another, and right angles are defined previously. And then there's the parallel postulates. And it's not important for the sake of today's talk, but it basically says that if we have 2 lines and we have another line crossing them, and if you look at the sum of the 2 interior angles on one side, and that sum of interior angles is less than 2 right angles, then those lines, if extended indefinitely, will eventually intersect. And so these are all of the starting points of Euclid. Again, don't memorize this. This is just a quick tour. What you actually start with are, I'm going to do some examples. So let's see how I am for time, 20 minutes. Okay. So we begin with the first proposition in Euclid. So this is Euclid Book 1, Proposition 1. And what it says is that to construct an equilateral triangle, on any finite straight line, on a given finite straight line. And this is a classic argument. It's a very beautiful argument. So the argument, the construction is as follows. Suppose that you're given some straight line segments. How do I know that there exists an equilateral triangle with this as one of its sides? And the argument is like this. Take this point as the center of a circle with this radius. And of course, drawing circles is very hard. So this is going to be an approximation of a circle. Then conversely, take this point as the center of a circle with this radius. These two circles will intersect at some point. Now, draw line segments from here to here and from here to here. Then, if you look at this line segment right here, it's a radius of the red circle. And so this line segment, let's call these points A, B, and C. So by virtue of being a radius of the circle, we have that AB is equal to AC. Similarly, by virtue of the green circle, we see that the line segment I was talking about the red circle before, so I want to write CB. Now, by virtue of the green circle, AB is equal to AC. And by the common notions, two things which are equal to the same thing are equal to one another. So we also have that CB is equal to AC. Thus, all three sides of this triangle equal one another. Demonstration complete. So it's possible to construct equilateral triangles if you're able to draw circles and with compass and straight edge. Any questions about that? So this is a very famous classical argument. And again, I'm just showing you this as an introductory lecture. None of this is actually part of the course or examinable. But we're going to see. There's a point that I'm getting to. Okay, so I want to show you what goes on in the book later. Then you have something like Proposition 35 in book 1. And what Proposition 35 says is that parallelograms which are on the same base and in the same parallels share the same base and in the same parallels equal one another. And so what does this proposition say? This proposition says that suppose that I have some line segment here, and suppose I have a parallel line segment here. So these two are parallel. Then suppose I construct two parallelograms sharing this as a base. Then my claim is that these two parallelograms are equal. So to illustrate the hypotheses, we have that this line is parallel to this line. This line is parallel to this line. And this line is parallel to this line. And to give some labels to this diagram, let's call this A. Let's call this actually A, B, C, D, E, and G. So our claim is that the figure A, B, C, D as an area is equal to the figure B, E, F, C. Okay, how is this proven? Well, one thing that happens is that if you look at the fact that these two lines are parallel and these two lines are parallel, then we know that this angle right here is equal to this angle right here. So this is proposition 35. There are 33 propositions between 1 and 35, which you haven't seen, but we're able to conclude that these angles are equal. Then another thing that we're able to conclude is that the line segment AD is equal to the line segment BC. Again, by lemmas about parallel things. And similarly, this is equal to the line segment EF. Now, what happens is that when two things are equal, you can add a common thing to them. So what we add is the line segment DE. And so we obtain that the line segment AE, this line segment up here, is the same as the line segment DF in length. And similarly, we have that BA is equal to BC. And so what we have is two triangles. Consider the triangle ABE. This triangle shares two sides and the same angle with the triangle CDF. So to shade it in I suppose a different color, this triangle right here is equal to this triangle right here. Now, what you can do then is from these two equal triangles, take this smaller triangle right here, subtract DGE. And so we obtain this quadrilateral right here and this quadrilateral right here, and then take BGC and add it to both. And then what do you obtain? On one hand, you obtain the first parallelogram. On the other hand, you obtain the second parallelogram. And thus both parallelograms are equal. That finishes that argument. So this is this should give you an idea of what Greeks mean by equal and the types of arguments that they have. And now I'll just sketch the rest of the theory that they had when it comes to areas. After this, they show that if you have any triangle, then if you draw a parallel line right here, that triangle is equal to the right triangle that has a right angle with a base like this. That follows pretty easily from this result about parallelograms. So you can sort of slide the triangle up top up to here. The next result says that a triangle is equal to half of the area. A right triangle is equal to half of a rectangle with the same sides if you have a right triangle. And then this is believable. This part equals this part. The next result that they have is that if you have any rectangle and you give any other base, then it's possible to construct a rectangle on that base whose area is equal to this one. So in other words, can construct given a rectangle, to construct an equal rectangle, in other words, equal area rectangle, on any other base. And so what happens then is that you have this notion, and this is a very important notion, of rectilinear area. And a rectilinear figure is any figure that's cut out by straight lines. So suppose all of these are straight lines, and I have a figure that looks like this. Then what happens whenever you have a rectilinear figure is that you can take your figure and you can cut it up into triangles. Then you can, so that looks like a quadrilateral. I should draw a line segment right here. And now I've taken this figure and I've cut it up into triangles. Now the previous results say that for each one of these triangles, I can take them and I can transform them. Let's say I fix this base. And let's say I give all of these triangles numbers. So let's say this is 1, this is 2, this is 3, this is 4, this is 5. Then I'm able to convert every single one of these triangles into a rectangle sharing this base. And in other words, I'm able to stack them. So I should draw it like this. And then the final result says that any rectangle is equal to a square. So in other words, given any rectangle, I'm able to construct a square of the same area. Now, all of this sequence of results, what does it say? The moral is that given any rectilinear figure, to construct a square of equal area. And why is this important? Because we have this notion that area is something, that area exists. When you have a figure, it looks like a figure has an area. But what does it mean to say that a figure has an area, right? Okay, never mind. Yes, sorry, I was looking at a direct message. So, right. Well, how do you know that your notion of area is substantiated? You say that you can talk about areas, but how do you know that someone like Parmenides won't come around and say your notion of area is self-contradictory? I can find plenty of holes in your notion of area. Remember, Greeks like to argue a lot, and finding holes in notions is something that they're experts at. And their entire theory is built around avoiding holes like this. Well, then, if you want to know that your notion of area has some secure foundations, this result really substantiates that. It says that if you have any rectilinear figure, you can convert it to a square. Well, what does that mean? That means if I have another rectilinear figure, I can convert that to a square as well. And then I can take this square and I can compare it to this square, right? And then I see that one square is bigger than the other square. So in other words, I can compare areas. Given any two rectilinear figures using compass and straight edge, I can tell which one of them has the bigger area. And the fact that I'm able to compare areas says that my notion of area has some substantiation. I might know what I'm talking about when I'm talking about areas, because when I talk about areas, I can compare them. And this is where the real story of this lecture finally begins. This notion of area, so this existed around 500 BC. So this is circa 500 BC. You have all of this theory. And all of this theory, ignore these parts, gives you some secure starting points for geometry, some axioms, some definitions of what you're talking about. And just using compass and straight edge constructions, starting with results like the two that I showed you, you're able to say that any figure cut out by straight lines is equal to a square, and any two squares can be compared. So any two rectilinear figures can be compared. Now, here are the two foundational crises that arose around 500 BC. So this is where Greeks started to get worried. And the first one is the problem of the comparability of curvilinear with rectilinear areas. So what does this mean? An example of a curvilinear area is a circle. It looks like a circle has an area, right? If I say that a circle has an area, then that sounds reasonable to all of you. But is the notion of area for circles the same as the notion of areas for figures bound off by straight lines? Can we even compare them? What does it mean? Maybe these are two completely different notions of area that have nothing to do with each other. How do you connect both of these notions? And again, remember, the Greeks are trying to find secure starting points, and they're beginning to be worried because they have a really good theory that lets you account for all rectilinear figures. But that theory says nothing about circles. It says nothing about curvilinear areas. So that's a bit of an issue. And then the second foundational crisis is the Pythagorean theory of proportions. So there's a very famous story that's completely false. And well, the true part is that the Pythagoreans were essentially like a cult. They really believed in numbers. By numbers, I mean whole numbers, 1, 2, 3, 4, 5, 6. And they founded a theory of proportion. So you can say that something, line segments, if you fix some line segments, then you can talk about 2 line segments. Or you can talk about 3 line segments and then define multiplication. And they also defined ways to divide a line segment into any number of line segments. So let's say I want to divide this into 3 line segments like this. And so really, they had a theory of rational numbers, sort of a theory of rational numbers. Now, the totally false story is that at a certain point in time, someone asked, well, you have a square. Let's say this is a square. These are unit side lengths. So the Greeks, by the way, did not have real numbers. They most certainly did not have real numbers. They did not have a number line. So this is the incorrect way of saying it. But we know, for example, from the Pythagorean theorem that if this is a square with a right angle, then this side length is the square root of 2. And the square root of 2 is not rational. For AB natural numbers. Now, for them, what it meant is that this could not be admitted into the theory. So this is true. This is a discovery that they made. The false story is that the person who made this discovery, it was held as a close secret. And he was so moved that the world needed to know about this that he said that he'd say it. And so he was thrown off a ship and murdered. And he was the first martyr to mathematics because he was going to spread the secrets that the square root of 2 is irrational. And this was this drastic thing. It was a shocking thing. Our entire theory of proportions doesn't account for this. But that's false. But it is true that the Pythagoreans had a theory of proportions, and they knew that their theory of proportions could not account for the proportion of the diagonal of a square to its sides. So this proportion was not admitted. And so you have these two crises. The first is that, okay, let's say we have a notion of length. Well, we like to form proportions of lengths. And we have this great theory. It really works, except for the fact that it can't account for this example. And then the other foundational crisis is we have two notions of area. And we think that we think that everything is area, like area should be a thing. We should have an understanding of areas. But are we really sure that areas bound by circles are even categorically the same type of notion as areas bound by straight lines? And so in the course of these two foundational crises, both of them come to head in a central problem. And this central problem encompasses both of these crises simultaneously. And so this was a conjecture. And the conjecture said that two circles are to one another as the squares on their diameters. So what this means is that suppose that I have two circles. And suppose that these two circles have a diameter. And suppose that I construct a square on this diameter. That is supposed to be a square. And also, those are supposed to be circles, although they certainly don't really look like circles. It's hard to draw circles. I mean, really, unless you have a compass, but circles are hard. Okay, so the leading conjecture, and this really connects to how you would compare areas, it said that these two circles, they do have a ratio. And that the ratio of those two circles is the same as the ratio of these two squares on their diameters. So that connects two things. That connects the idea of comparing areas, curvilinear and rectilinear areas, and the theory of proportions. And so both of them come to head into this problem. And you have all of this theory that I described before about finding, and to find a square of a given area is called to find the quadrature of a figure. So at 500 BC, they were able to find the quadrature of any rectilinear area. And right, I should also mention the other thing. There was, I suppose, 3 prime, the problem of squaring the circle. There was the question of, is it possible to construct a square whose area is equal to the square of a given circle? And most people thought that this was impossible. Whoops. And the people who thought that this was impossible were right. It was proven many, many centuries after this, in the 19th century, that it is indeed impossible to construct the quadrature of a circle using compass and straight edge. Now, if this problem had a solution, then we'd be able to compare circles to squares or to any rectilinear figure. But it looked like this problem did not have a solution. And so that's why the problem of comparing curvilinear to rectilinear areas remained open. Right. And so this remains an open problem for 200 years. And now we finally get to the story about this lecture, the point of this hype lecture. And it's been going on for a bit longer than I expected. No, I'll just go, yes, it'll be a bit 15 minutes longer than the hour. Finally, we get to our hero. Enter our hero. And his name is Eudoxus. And so after this remains an open problem for 200 years, Eudoxus comes along and essentially in 2 pages resolves both foundational crises and solves this problem. So in 2 pages, he solved everything. Now, how did he do this? And there are a lot of things that you can say about his arguments. I gave this lecture an intro to proofs course. And in that course, this lecture was twice as long. It began with an hour on Greek philosophy, and it actually talked about Parmenides' arguments. And it carefully scrutinized it and said, what techniques of arguing did Parmenides invent in On Method? And then what techniques of argument did Eudoxus invent in his proof? So we're going to go into that in a bit less detail, but we're going to see that this is actually going to be an argument by contradiction. And the beauty of an argument by contradiction is this. Eudoxus knows that he has area. He figures something out, and he's going on an ego trip. So he's really sure that he now has a firm notion of area. He has found a foundation of area. This completes the theory of area. He has area. The notion of area belongs to him. So he's founded it. And he's so certain that he's founded it. And he's so certain in all of the foundations of Greek geometry, which again, remember, they're made so that someone like Parmenides can't come along and poke holes in them. And he's so certain in them that he says that, well, if I can find a hole in something, so if I suppose something and then I derive a hole from it, it's impossible to derive a hole because the foundations are so secure, because I'm so sure in what I've done. And so the assumption that led to this hole must be false. And anyway, that's a bit of a digression, but you can say that the technique of argument that he uses, it really expresses incredible, extreme confidence in the foundations that he laid out. So what were these foundations? How in 2 pages can you resolve this problem of relating circles to areas, solving the theory of proportions that the Pythagoreans couldn't get for 200 years, and resolving the problem that 2 circles are to one another as the squares on their diameters? How does he do this? Before I tell you how he does it, are there any questions? Okay, let's get to it. Here is the Eudoxian theory of proportions, and this is genius. This is truly 2 pages that are completely genius. This is incredibly mind-blowing stuff. So first off, the Greeks were well aware. I should draw it right here. When do 2 things have a ratio? Let's say you have a rectangle and you have a line segments. Should a rectangle and a line segment have a ratio? Or similarly, should a line and a point have a ratio? Well, you had people in the Eleatic school. So Parmenides was an Eleatic philosopher, and you had several followers of Parmenides, such as Zeno. Zeno has all of these paradoxes of motion. The tortoise and Achilles and the tortoise, about covering, if you want to cross an area, you have to cross half of it, and then you have to cross half of the remainder, and then you have to cross half of the remainder. And so in order to get from point A to point B, you have to traverse infinitely many lengths, and that's impossible. And so motion is impossible. And this is in the lines of Parmenides, where Parmenides also argued that motion was impossible. But in less mathematical terms, he had a much more subtle philosophical argument for why change was impossible, why distinction was impossible, why everything was uniform, shapeless, and changeless. Okay, and so you have all of these arguments by Zeno and subdividing things, and the Greeks are really aware of this. This is like old news. This is 200 years old. They know that if you say that a point has a ratio to a line, or a line segment has a ratio to a square, in modern terms, which the Greeks didn't have, this will be analogous to dividing by 0. And the Greeks know that you can't admit things like this into your theory of proportions. They have 200 years of experience that if you're not careful enough and you say that those two things have a ratio, followers of Parmenides are going to come at you with their fists borne out and say, oh, all those holes, so many holes. So you just don't want to do this. You do not want to say that these two things have a ratio. So then what does it mean for two things to have a ratio? No one knows until Eudoxus comes along. What does Eudoxus say? Eudoxus begins with the following definition. Two magnitudes are said to have a ratio to one another when multiples of each can exceed the other. So what does this mean? Well, so for example, we have this idea that a circle and a rectangle have an area, right? Let's draw a smaller circle. Well, so how do I establish that the notions of area are the same thing? Well, if I take a circle and I just paste multiple copies of it, in other words, I take multiples of the circle and I add them together, and you can add them in a way that they intersect, it's possible to cover the square in circles. And similarly, it's possible to cover, in this case, it's a bigger circle, the circle in squares, rectangles. Remember that you had in your common notions, the whole is greater than the part. So to exceed something else, well, one way of showing it is that you have something that contains something else. So if you take multiples of the circle and just paste them together, this diagram right here shows that this circle has a ratio to this rectangle, because some multiple of the circle is capable of exceeding the rectangle, and some multiple of the rectangle is capable of exceeding the circle. And so then you might ask questions like, well, do a line, segment, and a point have a ratio? Well, they shouldn't. And you can ask, does Euclid prove that they don't? Well, Euclid doesn't, but Euclid doesn't care about proving that they don't have a ratio. Euclid cares about having a theory where someone like Parmenides can find holes. And someone like Parmenides is going to be able to find holes if you can prove that they do have a ratio. So in other words, if you can prove that some multiple of a point makes a line, well, it looks like that doesn't happen. And so I'm pretty sure that it doesn't happen. And so I'm just going to be pretty confident in my theory that no one's going to come around and show that multiple of a point can exceed a line. And then I'm not going to run its problems. So again, it's about being confident that no one is going to find holes in it. So it's not important to show that they don't have a ratio, but it's important to be pretty sure that no one's going to be able to show that they do have a ratio. And so this is a really, really clever definition. It completely eliminates the case of considering ratios of things like lines to points. Whoops, where is, okay, here is my. It completely eliminates this situation, and it establishes that something like a rectilinear figure and a curvilinear figure have a ratio. Okay, and now comes this really, really clever definition. Let's see, a question in chats. Is there a group me? I don't know what group me is, so no. Okay, now here comes the really, really clever argument. Oh, actually, maybe I might create a piazza. I might create a message board. I will create a message board. That's a really good point. I should create a message board. I haven't thought about that. I will. Okay. And remember, this is the hype lecture, so this isn't part of calculus, but we're going to see the relationship to calculus in a while. Here is the really, really clever idea. What does it mean for two ratios to be equal? So suppose that you have four magnitudes, A, B, C, D, and suppose that A and B have a ratio and C and D have a ratio. So I can consider the ratio of A to B, and I can consider the ratio of C to D. And then if those ratios are the same, I'll write it like this: A is to B as C is to D. So here is how Eudoxus defines what it means for, if you have four magnitudes, what it means for the ratio of the first to the second to be the same in the same ratio as the third to the fourth. So what does it mean for AB to be equal to, or in modern terms, we'd say this is what it means for A over B to equal C over D. But remember, the Greeks didn't have numbers. They had Pythagorean numbers, but they did not have real numbers. And you're going to see from this that the Greeks did not need real numbers because of this completely mind-blowing trick. Modern mathematicians and set theorists hates them. Learn how with one simple trick. And the trick is this. So imagine that in the case of lines, that you have a length A. And imagine that these are two columns, two Greek columns, standing in a line. So Greeks have a lot of columns in their architecture, right? Now imagine that I continue placing columns at equal line segments. So let's imagine that I continue this line. And I continue placing equally spaced columns. Right? And then similarly here, I take this line, I continue it, and I imagine placing equally spaced columns. Well, then look at this. So let's call this magnitude A and let's call this magnitude B. So A is less than B, right? Because if we look at A, we can put it here and it's a part of B. So it's a part, the whole is greater than the part. So A is less than B. Now let's look at something like 2A. Well, 2A is greater than B, right? If I look at two columns of A, that's bigger than one column of B. Then I have something like 2B. Well, that's also bigger, 1, 2, 3, than 3A, right? And so this is the most insanest thing ever. The notion of a ratio for Greeks was the results of all of these comparison tests. So the ratio of A to B is the information of when it, so you compare NA to MB. And then you say MA question mark MB, where question mark is either less than, greater than, or equal to. And the data of which one it is for every single pair of numbers, sorry, that should be an N. There are two different things, is what a ratio means. And so then you have, when are two ratios equal? Well, so there's this problem of comparing apples to oranges. A's might be areas, B's, C's, and D's might be lines. Or these might be curvilinear areas and these might be rectilinear areas, which we're not going to a priori assume are comparable. Well, you can compare A's to B's and you can compare C's to D's, but you can't compare other ones. Well, that's fine. We say that you can compare then things like C and D. Well, C is less than D. If we look at 2 times C, that's greater than D, if these things are in the same ratio. And so if the results for every single pair of numbers are equal, then we say that A and B are in the same ratio as C to D. Well, the Greeks didn't like writing through formulas. They didn't have algebraic notation. And so in sentences, they said magnitudes are said to be equal, to be in the same ratio, sorry, the first to the second as the third to the fourth when, if any equals whatsoever are taken of the first and the third, whenever any equal multiples, whatever, are taken of the first and the third, and any equal multiples, whatever, are taken of the second and the fourth, then the former equal multiples alike exceed, alike equal to, or alike fall short of the latter equal multiples respectively taken in corresponding order. That's a single sentence and it's a complete mouthful. But the idea is this, it's the idea of columns, Greek columns, evenly spaced. And the question of, well, if I take 3 spaces here and I compare to 2 spaces here, which one's bigger? And that's a piece of information. It can be 3 things. They can be, ones can be bigger than the other can be bigger than the first, or they can be equal. And so all of those pieces of information, that's what constitutes a ratio. And 2 ratios are equal when all of those pieces of information agree. And this is really mind-blowing. This is why the Greeks did not need real numbers. For us, we divide 2 things and we get a number, and we say we can compare numbers, but the Greeks didn't have numbers. Instead of numbers, they had this collection of information to form ratios. And this definition let the Greeks get away without having a number line. And then we're going to see that this course is Calculus B, that what Eudoxus does next into proving the proposition. So this constitutes the Eudoxian theory of proportions. These are the central definitions in that theory. Then we're going to see that what Eudoxus does is analogous to calculus. It's going to be analogous to integral calculus, which is the subject of this course, but it's not going to be calculus. It's going to be completely different from calculus because it doesn't have real numbers. Instead, they have this theory, and when you have this theory, you don't need calculus. So I'm going to show you how you can do stuff without calculus, and this is going to let us appreciate what calculus does and the history of calculus. Okay, finally, let's get to the propositions. By the way, any questions? Okay, my goal is to finish this in 15 minutes and then move on to the course. So then we get to, so these are in book 5 of Euclid. These are book 5 definition 4 and book 5 definition 5. Now in book 10, proposition 1, there is something called the exhaustion lemma. And I'm going to read it, and then I'm going to explain what it means. So reading it, 2 unequal magnitudes being set out, and then the asterisk here is magnitudes with a ratio that have a ratio. So it's not like a point in a line. It's not apples to oranges. It's lengths to lengths or areas to areas. Then if from the greater is subtracted a multiple greater than its half, a magnitude greater than its half, and from this magnitude greater than its half, and this process is repeated continually, then there will be left some magnitude less than the lesser magnitude set out. So what does this mean? So the Greeks didn't have numbers, but let's do an exercise. So these are going to be real numbers greater than 0. And I'm going to consider the number something like 1024 and the number pi, which is approximately equal to 3.14. So 1024 is bigger than 3.14, right? So I would like to, can anyone name a number that's slightly less than half of 1024? That's greater than 0. Anyone? I'd prefer some people spoke. Let's get into the habits of speaking during lecture. Okay, come on, someone unmute themselves, please speak.
Would 512 work?
Okay, yep. So 512 is exactly half, let's say 511. Good. Let's do this again. Can anyone give me a number slightly less than half of 511? Someone else. This is an exercise in getting people to unmute their microphones. That's the point. Okay, more people, unmute yourselves. A number that's slightly less than half of 511.
253.
Good. Again. Unmute yourself time.
120.
Good. Again.
100.
Sure, but 100 isn't less than half of 120. So we can say 100, but let's round down. Let's do less than 60. What's less than 60?
55.
Good. Okay, what's less than half of 55?
20.
Good. And then less than half of 20?
15.
15 is more than half of 20.
5.
7.
7, good. And again?
3.
3. Okay, look what happens. So we've kept dividing it and we've gotten to 3. And 3 is less than 3.14. 3 is less than pi. And so what's this? This is called the exhaustion lemma, and it's the key example. And the way that it's proven is that the hypothesis is that you have two magnitudes that have a ratio. In other words, some multiple of the first is capable of exceeding the other. And using this assumption that you can make each multiple bigger, some multiple of this is bigger than that, and some multiple of that is bigger than this, you essentially get the process that if you take more than half of it away each time, in a finite number of steps, you're going to get something less than this number. This looks like a limit, but there are no limits involved. This is talking about a finite process. This is talking about what we just did. If we name any two numbers, that's a modern way. Greeks didn't have numbers. They had magnitudes where you'd actually take half of a line segment. If you repeatedly cut out more than half, then you're eventually going to get something that's less than any other comparable magnitude set out. So that's the exhaustion lemma. And that's a really big ingredient into all of this. Okay, everyone, thank you for unmuting yourselves. That was good. And now later, so this is the hype lecture again, but when we get into the material proper, I would like questions as much as possible. Okay, so now we understand what this says. Finally, we're going to get to Eudoxus's argument that two circles are to one another as the squares on their diameters. But before that, so Eudoxus's proof. So he begins with a lemma. And this lemma is book 12 of Euclid, proposition 1. And what the lemma says is this. So I'm going to copy it out. Similar polygons inscribed in circles are to one another as the squares on the diameters of the circles. Okay, so what does this mean? I'm going to bring up again what our overarching goal is. If we have two circles, and these circles have diameters, now that we have a theory of proportions, we can talk about the ratios of the circles to one another and the ratio of the squares on their diameters to one another. But before tackling that case, he considers this. Suppose I inscribe some polygon inside of the circle. Inscribe just means that all of the vertices of the polygon lie on the circle. And then suppose I inscribe another polygon here, and this polygon is similar, which means that all of its sides have corresponding ratios to all of the sides there, and that the angles are the same. So this has the same shape as that. Then this is a rectilinear figure. So both of the polygons are rectilinear figures. And so this is comfortably in the theory of rectilinear areas using standard techniques like the techniques I showed you before. He proves that, let's say this polygon is P1, this polygon is P2, and then this square is D1 squared, and this is D2 squared. So this lemma says that P1 to P2 is the same as D1 squared to D2 squared. And the proof is just using standard techniques because we're still living in the world of rectilinear figures. We're perfectly comfortable. Remember, 200 years before Eudoxus did any of this stuff, you had a really good theory of rectilinear areas. So proving this is a cakewalk, relatively speaking. So now, using that lemma, here comes the main coup de grace of this. This is the main point, and this is the point that's going to connect to calculus. So here is the main theorem. Two circles are to one another as the squares on their diameters. Or even simpler, I can just say, I don't have to say two circles, I can say, well, all circles. So here is the shortest way to write it. Circles are as the squares on their diameters. And then the longer form would be talking about two circles. Two circles are to one another as a square on their diameters. So we have a theory of proportions. We have all of this. And now how do we show that two circles are to one another as a squares on their diameters using all of this theory of proportion? Okay, so here comes the incredibly beautiful thing. Let's say you have some circle. Then you begin by inscribing a square in that circle. Now, I can do a process where if I have any polygon inscribed in the circle, I can take each side, I can bisect it, I can draw a perpendicular going up to the circle, and then I can construct another inscribed polygon with twice as many sides. So let's say that's the let's say that this is circle 1. So the red thing is going to be C1. The blue thing is going to be P1, 1. So it's going to be the first polygon approximating it. The green thing is going to be P1, 2. So it's going to be the second polygon approximating this. And the key result is this. So suppose this is some arc of the circle. Then suppose that I have a side of anything. Suppose I bisect that side and I drop a perpendicular here. And that I construct these edges. Then what I do is this. I complete this to a rectangle with the top side tangent here, or in other words, parallel to the bottom side and touching the top of the circle. Then look at what happens. This blue figure down here, this shaded figure right here, is what this figure right here is half of the red figure of the outer rectangle. Why? Because I can split this into two rectangles and I've literally divided it. It's exactly half of the rectangle. So you can see you can see that this is exactly a side dividing it. So this is half of this rectangle. So the sum of these two triangles is half of the red rectangle. So now imagine something like C1 minus P1, 1. So in other words, imagine the area that's left over from the circle when you take away this square. Then if I imagine C1 minus P1, 2, then what I've done is that I've taken away more area. And the amount of area that I've taken away is half of the area of the red box. But the area of the red box is bigger than this segment here, which was the segment of area that I originally had in the difference between this. So in other words, if I complete this process, and in general, I have P1n, this is the nth step of dividing these sides in half. C1 minus P1n is, so this is, and then, okay, if I compare this to C1 minus P1n plus 1, so in other words, the next step, then this is less than half of this area. So this is less than half of this. So in other words, by going from one step to another, I take away more than half of the area that's remaining between this polygon and this circle. What does that mean by the exhaustion lemma? That means that if I have any other area, then by taking away more and more of the circle, by expanding this polygon that's approximating the circle, will eventually arrive at some area that's less than any other area that you give me. So it's exactly this thing that we were doing before with taking away more than half, but this is a very clever way of taking away more than half. It says that if I begin with an inscribed approximation, and then I keep taking away this by doubling the amount of sides that you have at the midpoint, then that takes away more than half of the area. So this is some way to get all of these polygons to fill up the entire circle. And that's why this is called an argument by exhaustion. You're exhausting the area of the circle. Okay, so we have this idea that we can construct these polygons P1n. So let's draw the circle and let's do the argument now. So you have, let's use consistent colors. Let's say this is C1. This is C2. And both of these have a diameter. Let's call the diameter is D1, and let's call this diameter D2. And then you consider the squares on their diameters. So this is D1 squared, and this is D2 squared. And then the claim, so this is what we want to show, is that C1 is to C2 as D1 squared is to D2 squared. So this is our goal. Okay, now what do we know? Well, if I consider P1n, then that is similar to P2n. In the first case, if I inscribe a square in here and I inscribe a square in here, then they're both squares and all squares are similar. Then if I divide the sides, they're similar. And so I have this lemma. And the lemma says that similar polygons inscribed in circles are to one another as their squares on their diameters. So I know that D1 squared is to D2 squared as P1n is to P2n. By the lemma. This is just the theory of rectilinear figures. This is the standard results available 200 years before Eudoxus goes. So here is what Eudoxus says. Here is the beauty of his argument. This is the proof by contradiction. He says, suppose C1 is to some area S as D1 squared is to D2 squared. So in other words, we have that C1 over S is equal to D1 squared over D2 squared. Then we can consider S versus C2. So we have three cases. Either S is less than C2, S is greater than C2, or S is equal to C2. I'm only sketching the argument, but you can say that in the previous results in the book, he establishes that these two things would actually have a ratio. And so if S is equal to C2, then C1 is to C2 as D1 squared is to D2 squared, and we're done. And so what he's going to do then is he's going to assume that either of these cases holds, and he's going to derive a contradiction. And that's going to show that both of these cases cannot hold. So we'll show that assuming S is less than C2, I get a contradiction. And then similarly for S is greater than C2. And I'm only going to show you one of these cases. And then in the proof in Euclid, he actually doesn't do the second case. He reduces the second case to the first case. But it's not instructive to show you how it's going to do that. So I'm going to show you how the first case is handled. Suppose S is less than C2. So in other words, suppose that C1 is to S as D1 squared is to D2 squared, and S is less than C2. Then I can basically consider the quantity C2 minus S. Well, this is non-zero, is a non-zero area. In other words, it's comparable to areas, any other area. And then I can consider C2 minus P 2n, right? This is an area. So if I take C2 and I inscribe polygons in it, and I keep inscribing polygons in it, the dot difference is eventually going to be less than any other area set out. Now, C2 minus S is a non-zero area. There's no such thing as a zero area. The Greeks don't have zero. If we look at what the exhaustion lemma says, it says for two unequal magnitudes in its hypothesis. Well, they are unequal magnitudes. Well, one is less than the other, which means that you can take a part away and you have something left over. Okay, wait, never mind. That remark about equal magnitudes isn't relevant. Sorry. Yeah, actually, it's a bit of a misnomer. Ignore that. Anyway, the point is that this can be made smaller than C2 minus S. So by the exhaustion lemma, I can make this difference be less than C2 minus S. I get some n so that C2 minus P2n, it eventually becomes smaller than C2 minus S. And so what does that tell us? Well, that implies that this thing is bigger than this thing, that S is less than P2n. And P2n, by the way, is an inscribed polygon in C2. So that literally lives inside of C2. So in other words, by the exhaustion lemma, I'm able to find some polygon, inscribed polygon that's between C2, S and C2. So one illustrative picture is, suppose that this is C2. Again, circles are hard. And then suppose that by sheer coincidence, S is a circle with the same center, which again, this isn't rigorous, this is just intuitive. Then what this lemma really says, what this argument says, is that I can find some inscribed polygon that gets between C2 and S2. It's going to be one of these regular polygons with sides number power of 2, which isn't what I drew. But by inscribing bigger and bigger polygons, you eventually get something between S and C2. And that's by the exhaustion lemma. Okay, and now it's just a couple of lines to drive a contradiction from here to here. So we have from before that D1, so we have that C is to S as D1 squared is to D2 squared. And D1 squared is to D2 squared as P1n is to P2n. So in other words, we have C1 over S is equal to D1 squared over D2 squared. This is using modern algebraic notation. In Greek, they would write it in sentences. So they didn't have the luxury of algebraic notation. Well, okay, so what do we get from here? They had a notion of cross multiplication. And so from this, it follows that C1 to P, sorry, and then this is equal to P1 N over P2N. By the way, here's a question. Can anyone hear the fans on my computer? Or is it getting filtered out? Because my MacBook is trying to land right now.
I don't hear
No, I don't
anything.
hear it.
Okay, good.
No.
Good. That reassures me. So anyway, by cross multiplying, we get that C1 to P1 N is the same as S over P2N. Okay, but here's the thing. P1N is less than C1. Why? Because P1N is an inscribed polygon in C1, right? Now, remember, what does it mean for two ratios to be the same? A ratio is exactly the result of all of these comparison tests, right? So let me just quickly check. Okay. So if this ratio, this comparison between these two things resulted in a less than using coefficients 1, 1, then that implies that if I make the same comparison between the bottom here and the top here, that I should get the same results by the definition of the ratio of what it means for two ratios equal, for two ratios to be equal. Well, okay, so what does that tell me? That tells me that S is bigger than P2N. But what did I have here? But I had that S was less than P2N. And that's a contradiction. So in other words, by bringing this area over and then comparing that area to this circle right here, and then bringing it back, I get the opposite containments. These two statements are incompatible. I can't have this is strict inequality in this direction, while having strict inequality in this direction. That's a problem. That's a contradiction. That's a hole. It can't be the case that what I assumed is true. And what I assumed was that S is less than C2. So it's not the case that S is less than C2. And then he handles, so this can't be the case. And then this case is reduced to this case as well. And so by similar arguments, and another way to argue it would be by considering polygons outside of the circle. So imagine I took this and then I started inscribing polygons outside of the circle. So I inscribed it in a square. That side's supposed to be touching. And then I imagine I did the same thing again of dividing this area, adding more and more sides. And then I kept doing this over and over again. So in other words, outside I take polygons and they close in on the circle. And then from inside I take polygons and they close out of the circle. Then this idea that these consume all of the area that's left over outside and consume all the area that's not filled inside, that shows that you're getting this ratio by these approximations. And so I derived a contradiction here, you derive a contradiction there, and then that's done. And so Eudoxus does this in 2 pages. So what I've just shown you, that solves 200 years of open problems. For 200 years, people thought about how to do this. And then Eudoxus comes along and he has this great idea about this theory of proportions. And he has this great idea to do the first proof in the existence of mathematics, the history of mathematics by contradiction, inspired by Parmenides' first argument by reductio ad absurdum. And that closes 200 years of issues. So this is 2 pages when it's written up, along with these definitions. And bam, Eudoxus, young mathematicians, 20-something years old, 200 years of open problems, just resolves them. Okay, so that's the story. We're now actually going to begin calculus after taking a break, of course. We definitely need to take a break. That was a very long lecture. And I really hope that all of you didn't get exhausted by that, pun intended, because we're actually going to need to pay attention for the next half. So let's take a 15-minute break. Let's say we resume at 7:45. So resume at 7:45. I'm going to make myself some coffee in that time. And just as a quick remark, so this is what it means for Eudoxus to have area. He's sure that the concept of area, now it's established, now it's founded. Would curvilinear and rectilinear areas be compared? Are they even philosophically the same thing? Bam, not only did I just create a theory of proportions, but I also solved the problem about comparability of curvilinear and rectilinear areas as just like the definition of what it means for two things to have a ratio. And I resolved this problem about two circles to being one another as the squares of their diameters. Now, in a book like if you look at the book that's usually used for calculus, well, they usually use OpenStax. But I think when they were using a book like Pearson, it's one of the big 500 pages bulk store calculus books that cost $200 that they sometimes make you buy, which is a scam. Don't buy books, by the way. LibGen. This right here, LibGen, look it up. It's a website where you can pirate any academic book. You should never buy textbooks. You should download them from LibGen. Pirate books here. Some of you may be first years. Buying textbooks is a scam. Anyway, sorry, getting back to the topic. In one of those bulk books, they say that Archimedes, first off, that's wrong. It was Eudoxus who had this result, not Archimedes, proved a formula like A equals pi r squared. That statement is fractally wrong. So this result establishes that you can cross multiply, and then you have that the ratio of any circle to its square on their diameters, all of those ratios are equal. So that does something like defining the number pi, but remember the Greeks don't have real numbers. So it's not a formula. Well, they show that A over r squared is a constant. Or in other words, all A's over all r squares are equal. So that does something like defining pi, except for the fact that they don't have numbers. So it's really wrong to say they proved a formula like A equals pi r squared because there was no such thing as pi. What they did have is exactly what I spent the last 1.5 hours describing, with the theory of proportions. They didn't need calculus. They didn't need numbers. They just had, Eudoxus had all of these ideas and he put them together. Okay, none of this is going to be examinable, but you're actually going to see that this idea of taking areas from the inside, taking areas from the outside, and using them to approximate area is going to be a central question in this course. This course really is going to be about finding areas. It's going to turn out that this is a very deep problem and that almost all of the applications of calculus use the problem of finding areas. And that's why this hype lecture is going to be relevant. And we're going to see that when we define the integral, which is the area under the curve, these Eudoxian ideas are going to rear their face and come into light. Okay, I'm going to take a break and mix myself some coffee. So see you all in 10 minutes. So what we just did, that was one of my specialty lectures. That was my Eudoxus lecture. And I hope that the Eudoxus lecture was entertaining. You're going to see a bunch of parallels with calculus and Greek geometry, but you're definitely not going to be examined on Greek geometry. So the course starts now. Okay. And so this is the very important thing. I should say some things about course policies. So I looked at my first assignments and I think it's too hard. I think I made the first assignment too hard. I would be really impressed if anyone solved the assignment entirely. So that brings me to my main thing. This is my promise to you. This course is going to be curved into the stratosphere. Now, why is this happening? It's going to happen for a very specific reason. So this class is going to be very different from a 500-person calculus course. I'm sure that all of you, unless you're incoming students who are about to start university next term, or high school students, that's cool as well, have been to a large 500-person class, and those classes suck. They don't hold students in really high esteem, and they're very much jump through the hoop courses, where you're expected to do a bunch of things. They're generally not curved or not curved substantially. And it's just, I mean, even something like when the pandemic started, the calculus class that I was TAing for that term, we ended up reporting, like actually filing reports on something like 15% of the students for cheating during the course of the final exam. So just to be clear, that's not happening in this class. Oh, okay. I should also mention, Chegg is banned. Like super hard banned in this course. You are not allowed to access Chegg at any point for any purpose relating to calculus. Really don't. Okay, is there a question? Are exams and quizzes open notes? Yes, I am going to have, so I have not decided whether I am going to have take-home exams or 2-hour exams. So my exams are going to be open notes. And there's going to be a ban from accessing online notes. So it's going to be course notes only. You're not going to be able to look answers up online. But either way, it's either going to be a 24-hour exam or a 2-hour exam. And which one of those two formats I go with is going to depend on what I think about the homework submissions and how things are going. But I can tell you that the exam is probably going to occur on the Monday of the 4th week. There are 5 weeks in the semester. And then on the Monday of the 6th week, we're going to have the final. Do I provide answer sheets? Yes, I am going to provide answers, but that means that I'm going to have to be strict with homework deadlines so if I'm going to upload the answers. Last summer, I did not. Last summer, I taught a course which was almost exclusively automatically graded. It was more of a programming class than a math class. Not exactly. It was about writing proofs on a computer. And because I had a grading server that would automatically grade people's homework, I didn't enforce deadlines. And this led to a bunch of people procrastinating, as does happen. So I really don't like enforcing deadlines, but you know what? I am going to enforce deadlines in this course, and that will let me post answers. Okay, right. So I am now going to get to this thing. This course is going to get curved to the stratosphere. Why is this course going to get curved to the stratosphere? So I was making this point that a 500-person class is very different from a small section with 40 students. When you're an instructor in a course with 500 people, your primary objective is disaster management. You want to avoid any situations if there's something that will cause a large amount of students to complain. So in other words, if there's a problem on an exam that's miscalibrated, you are dealing with a large number of, it's just too much work. You want to minimize the work that you have for yourself, and you want everything to run like a well-oiled machine. The large courses have a course coordinator, and the course coordinator's primary job is to ensure that everything is smoothly oiled and that there aren't hiccups, or that hiccups are mitigated. There are going to be some hiccups, but that leads to a really formulaic course structure. And that leads to a really gameable course structure. That leads to a structure where and looking up answers on Chegg is almost, what is going on? Sorry, okay, there we are. That was weird. That leads to situations where you're being asked to jump through the hoop, and using Chegg becomes a feasible option. So I decided that I'm going to do something for the summer. So it's like you move into a new apartment and you ask yourself, well, what do I want to do with the place? Well, I asked myself, well, what do I want to do with this course? And I decided that I was going to limit myself to one central objective for what I wanted to do with the course. And the objective that I decided on is that I'm going to teach you how to write proper answers. So my personal objective is to teach you, get you all to write high quality solutions to mathematical problems. And so what do I mean by this? There is such a thing as a language of mathematics. When you write mathematics, this is an analogy that I keep making. Writing mathematics is like writing an analytical English essay. You have expressions, then you have equalities. Those are like the verbs in your sentence. And then you are presenting an argument. And what happens in large calculus classes is, I mean, I've graded a bunch of exams. I've taught calculus for 5 semesters in a row for a TA. And we get very low quality answers. We get like, they're bad. As far as treating mathematics as a language goes, it's mathematically illiterate. And my personal objective is that I'm going to combat this as much as possible. I want everyone to get to the point where they're writing very good, very clean solutions that are very well presented and conforming to the language of mathematics. This means that I am going to be incredibly strict about how you write your answers. This means that the answers that you would have written in a large 500-person calculus course are going to get a lot of red on them, and they're going to get a lot of points deducted, because that's a very low standard that you're being held to in a large course, which brings the difference between a large course and this course is that I'm going to hold you to a much higher standard, and I'm going to hold you in much higher esteem. And when you have high expectations placed on you, and when you're held in higher esteem, it's just a much more pleasant experience. And that's where we get to this promise that this course is going to get curved to the stratosphere. The assignments are going to be very hard. They're going to be less hard than the first assignment. I think the first assignment is too hard because I just introduced too many notions. And you're also, every single problem has the word show in it. In other words, I'm deliberately writing provocative problems that are going to force you to write. And I know that most of you are not able to write good mathematics. And yeah, you're going to submit bad responses, and they're going to get a bunch of red. And it looks like, oh, well, no, my grade on this assignment is bad. Well, that's where curving comes in. If I promise you that I'm going to curve this class very hard at the end, I can go hard and be very discriminating on assignments. The assignments, your grades are not going to be good, but that's only because otherwise you're just getting good grades and you're not improving factors and you end the course not writing good solutions. This way, okay, so what am I going to be satisfied with? If all of you just can put in enough effort, if I'm convinced that you've put in work into this class, I'm going to give you a good grade. So I want to see work and I want to see improvements. And that's what happens when you're held in high esteem in a course. It's not a 500-person calculus class. Curving is going to be very lenient, but you're also, I'm going to be stricter during the term. And that's because I expect more of you. And it's good to have more things expected of you. So I'm really, this semester very much is about writing proper mathematical solutions. They're going to be beautiful. They're going to be well formatted. They're going to convey a clear logical argument. You should think about it like writing an English essay. And I said, remember, this is 5 weeks condensing 16 weeks. So a reasonable amount of time to spend on this course is about 12 hours a week. Again, it's a summer course. It's a significantly condensed semester. It would be 4 or 5 hours a week regularly. 5 hours a week. How will we hand in homework? I will actually respond to several more of those questions. Right, sorry, we're getting on track. Right. Yes, so that is this thing. And okay, that also brings me to the point of why Chegg is super hard banned. So first off, I am going to make my questions as uncheckable as possible. But that's not an invitation to try checking because you will succeed. But if you copy answers from Chegg, it is going to be very obvious to me that you copied them from there. Also, because I have a departmental account and I'll be checking that. And I will take it personally if you copy answers from Chegg. This course is very much about having problems that are going to probably be harder than above your limits. You're not going to be able to finish these assignments fully. And if you just look at this course structure of the course being eventually curved at the end and me wanting to just see you improve in how you write mathematical answers, using something like Chegg completely breaks my course. And that's why it's not going to happen. You are not accessing Chegg this semester, and you're not looking up answers online. You are allowed to look up books. I recommended several books, and I'm going to be writing notes. But in general, I'm going to, since I'm writing notes, make my questions be so that there's a relevant example in the notes. And when you're solving homework, you generally want to go into the notes, look at what example is relevant, and then try and copy it. And then also, because of this thing that you're expected to spend about 12 hours a week on this course, again, you definitely shouldn't be taking more than 2 courses. So 2 courses in the summer should be a full 5-course load in regular through the year. Okay. Okay, let's time to answer questions. Are homework assignments graded for completion or based on the answers? Homework assignments are going to be very much based on, yes, I am going to be incredibly discriminating on the answers. It is going to be about how well you write up the answers. And because you're spending 12 hours and I only have 7 or 8 problems on the assignment, each problem is supposed to take more than an hour. And because you're spending so much time on a problem, you better have a good write-up at the end. What is a good write-up? Well, submit the first homework, get a bunch of red in response, and I'll tell you then. But also, I will give a bunch of examples in this lecture and in Thursday's lecture, and you should try and imitate what I do when writing up homework answers. Because again, my personal objective is to get you all to write good answers to homework problems. Okay. Do we get 1 assignment per week? There are 5 weeks, so it's pretty obvious that we're going to have 5 assignments. Also, assignments are worth 50% of the course grade. So I have a course website. I sent it to you by email, and the syllabus, the notes, and the first homework assignment are all on the course website. I'm going to be posting everything to the course website. So bookmark that. How will you hand in homework? Probably by Blackboard. The first homework assignment is out and it's due before the start of next Tuesday's lecture, so you have a week. And I'm going to create a Blackboard link soon. The syllabus is posted online to answer the next question. And do I have office hours? Yes. I am actually I strongly prefer to have by appointment office hours. And this is bigger than the courses that I've previously taught, which means that I might regret this and make them regularly scheduled. But by appointment office hours is pretty much the best arrangement that you can have for office hours, because that means that you should just send me an email and then I'll meet you whenever is convenient for you. Oh, okay. Finally, how to actually submit assignments. Well, yeah, I'm going to send an email about that. Because I'm really want you to write good quality answers and because I want you to spend a lot of time on your assignments, don't be annoying and upload pictures that are upside down or that are barely legible. I'm going to give you instructions on how to take very good pictures of a paper with on your phone. Specifically, there's an app, and the app lets you scan the page. It lets you format the page so that the rectangle is there, and I'll only accept submissions in PDF formats. I'll say a lot more about that. We should actually get onto writing, doing some calculus. Oh, by the way, does anyone want to mute themselves and ask any questions about course policies?
What if like adding an app takes up too much space on your phone? Like if you already have a bunch of apps.
Oh, okay. Well, it should be a pretty small one. It's But there are also several other ways. So I'm not saying that you have to use the app that I'm going to recommend by email. But I am going to say that I do want submissions that are single file PDFs and that the PDFs should look very presentable. This is reasonable. So first off, I should also admit that for this course, I was supposed to have a grader and my grader dropped out last minute. So I have to grade the assignments. This means this is bad. This is going to compromise the quality of the grading. I sort of did not sign up to grade, but it ended up happening because we don't have people who want to grade. So just please, 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 please don't make it hard on me. I already barely have enough time to prepare everything. And I want your assignments to be presentable. And I'll say more about them presentable.
And just to confirm, you're going to send out an email with all that information, right? With
Yes.
about the app and everything? Okay, awesome. Thank you.
And as for email, I am going to actually create, so emails sent from Blackboard to everyone enrolled in the course, they don't look very presentable because the Blackboard sending email feature is bad. So I'm going to pull everyone's emails from Blackboard tonight. And then I'm going to create a mailing list on Gmail and send them not via Blackboard, but just with Gmail so that I get better control of the formatting. If anyone isn't enrolled on Blackboard right now, then I might have to add you manually to that list. So if you're not getting emails, like if you don't get an email tonight, or let's say by tomorrow, with a bit more information, then I might not have included your email on the mailing list and I should add it. I'll probably make a post on Blackboard so that people can see it, but otherwise everything is going to be posted on the course website and then information is going to be distributed by email to the mailing list. Sounds good? Right. Okay, let's start with calculus. So I thought about how I should do this, and I decided that I'm just going to put all of the theory at the beginning of the course. This means that at the end, you don't like theory. Theory is a bit dry. Theory is hard to understand. But that means that it's better for you to be disappointed with me now than later if the ending of the course is good and I'm starting off with all of the theory and I'm starting off with the hard assignment. It's going to get easier probably, as in I will try and make it easier. But right, we are going to start with very abstract theoretical stuff. And then after we get all of the abstract theoretical stuff out of the way, we're going to do a bunch of examples. It's going to be less like the next weeks are going to be very concrete about how to compute integrals. Right now, my goal, and I probably won't get to it by the end of today's lecture, is to theoretically define what the integral is. So I talked to you before about how the Greeks defined area. Well, I'm going to tell you about what the modern definition of area is, or at least one modern definition of area. And so really, okay, let me just quickly set this up. Oh, okay. I would actually prefer that you did all of your assignments not on paper. If you have a writing application that lets you write it, or if you want to type your assignments up, then that's better because it's much more presentable and much more easy to grade. So I do your assignments in any way that you like, so long as it looks presentable. That's the main thing, right? So if you want to do it on an iPad note app, then that's actually going to make me happy because it's going to be much more readable than paper scans. I'm sure you agree, right? Good. Okay, let's start off with the material. So first off, I'm going to go slightly out of order from my notes, and I'm going to tell you what the central problem of calculus is. Suppose, so these are going to be my coordinate axes. Suppose that I have the plane, and suppose that I have some function f. Now, suppose that I have some interval, let's say from a to b. And I just restrict the function to be defined on that interval. Well, let's say I drop a line to the function here. And I drop a line to the function here. And I look at this region of the plane. So I can say that that region is an area. Region and area are synonymous terms. And I can define what points live in that region. But the word area has another meaning. Area isn't just a region. Area is also a measure of how much area there is in something, right? One way that you can think about it is, suppose that you're painting a wall. If you have a bigger wall to paint, you use more paint than if you have to paint a smaller wall. So the amount of paint that it takes is one very, very, very rough notion of what it means to take the area of some region. So the central problem is going to be for how to find areas that look like this. They are going to be areas bounded by the x-axis and some function. And this area is called, and this is a word that we'll be hearing frequently, the area under the curve. So I'll highlight that in blue. And so that's our goal for today and for tomorrow, to define what it means to take the area under the curve bound by some function. And now I should do one more clarification. Right now, this function is positive. It lies above the x-axis. Suppose that I have a function that crosses the x-axis. So like some parabola that looks like this. And suppose that my interval over which I want to take the area, the bounding points, this is my A, this is my B. I draw these lines up here. And then I shade this area in here. So the convention is that area under the x-axis is negative. So in other words, we want the difference of the area above the x-axis with the area below the x-axis. Okay, so this is just now our goal in this lecture. I showed you how the Greeks thought of area. I'm now going to show you how we think of area. And it's going to be a very careful definition. And this is the theoretical part. Now I'm going to be clear about something. This is not a class about writing proofs. This is a class about solving exercises. If you actually read my syllabus, and you should read my syllabus, I write that I think of calculus classes as essentially math gauntlets. It's about learning how to solve a bunch of exercises. The reason that we make you do calculus is because it's a really good class to just do general problem solving. So this class is fundamentally about learning how to solve some class of problems. Now the theory isn't going to be directly tested, but it's going to be very important for building intuition for solving those problems. But the problems aren't going to be writing proofs. So if I do any proofs, I'm not going to actually ask you to like recreate those proofs on an exam or prove similar things. A lot of my questions have the word show in it, which is not the word prove. And sometimes you might be loose on the boundary between the two, but really it's about writing answers to a formulated class. So in other words, the theory is there because I can't not do any theory. But the theory is auxiliary to actually solving the problems. Later, we'll be solving more problems, but I'm putting all of the theory first. Any questions? Okay, so that is just an orienting goal to our class. Now I'm actually going to get into a bit more detail and talk about a few things that are less relevant to this problem before I actually tackle this problem. Because in order to tackle this, I need a bunch of theoretical machinery. And that theoretical machinery is about limits. But before talking about limits, I'm going to talk about sets and general mathematical language. So sets are collections of things. In general, in math, every single type of thing lives in some sets. That looks like a completely vague philosophical platitude that doesn't correspond to something concrete, but I'm going to give you some examples. So for example, we have the set of natural numbers, which is written like this, the set of natural numbers. And what are the natural numbers? Well, the natural numbers are 0, 1, 2, 3, and then I'll say and so on. And then I enclose it in these curly braces. And this is the curly braces are often used to denote sets. So we understand what the natural numbers are. We learned them in school. We in fact learned counting in kindergarten. I made a very big point about counting in my previous course on logic. And okay, then we have, for example, the integers. This is the set of integers. And the set of integers adds to the set of natural numbers negative numbers. So I can write this as ... -2, -1, 0, 1, 2. The ... are vague, but you know what I mean. You know what I mean when I say 0, 1, 2, and so on. And you know what I mean when I say -1, -2, -1, 0, 1, 2, and so on in both directions, right? Now, what does it mean to treat them as sets? Well, I can write things like 0 is an element of the set of natural numbers. So this symbol right here sometimes when things overheat, things crash. So I like to save it frequently. This here means is an element of. So 0 is a natural number. That's how you read this statement. Similarly, you have -2 is an integer, right? So this is just language. I'm just adjusting you to some language. It's part of the language of math. So just accept those statements as me defining sentences that we would say in this course. Okay, then we have, for example, the set of rational numbers. And I'm now going to use set builder notation. So this is the set of all ratios A over B. And then I'm going to quantify this over something. So A over B such that A and B are integers. And so that B is not equal to 0. So first off, we all know what the set of rational numbers is. 1/2 is a rational number. 3/2 is a rational number. I should write this in Greek. -2 is also a rational number. It's -2 over 1. These are all rational numbers. And so the language that I use to write it is I say that it's all things of the form A over B, where A and B are integers and where B is non-zero. So this is just a matter of language. I can write an expression like this to define the set of rational numbers. Any questions? Okay, and then finally we get to the superstar of calculus, R, the set of real numbers. And defining what the real numbers are is actually very hard. And I can't do it right now. It's outside of the scope of this class, but we think of real numbers as points on a number line. So number lines, you've seen this picture before in school. Here's 0, here's 1, here's 2, here's -1, here's -2. And then I can consider points. So in my notes, the points that I marked are, for example, between 1 and 2, I have the point pi over 2. And then between 2 and 3, I have the point e. And these are both irrational numbers. They're transcendental numbers. They're not in Q. And transcendental means an even stronger property, but it's not important what that means for this class. And so the real numbers have no holes. And calculus really, it's about the real numbers. You're using properties about the real numbers. Although it's very hard to actually define precisely what the real numbers mean. So, okay. I said that in math, things belong to some sets. So whenever you have some notion, there's usually a set of all things belonging to that notion. We have a notion of natural numbers, and so there's a set of natural numbers. We have a notion of integers, and so there's a set of integers. We have a notion of rationals, and so there's a set of rationals. And we have a notion of reals, so there's a set of reals. Now, let's do a few more set theoretic constructions. You're familiar with this picture. Let's say this is the plane. And let's say I mark a point on the plane. And then let's say that this is 1. Okay, what are the coordinates of this point? Can someone unmute themselves and say it?
Two.
Yeah, exactly. And so you've seen this in school. So we have a plane and points on the plane have coordinates, right? So we're all familiar with this. Well, so we have this notion of points on the plane. That's an idea, and therefore there is a set to which it belongs. So there is a notion of ordered pairs. So I'll highlight this here. And therefore there is a set of ordered pairs. And this set is written as R cross R. The cross symbol looks like multiplication, but there's no multiplication going on. This is just a description of a set. This is the set of pairs. So this symbol right here, this means the set of pairs. So for example, and this again, this is just language. All I'm doing is I'm describing sentences that we can say in math. There's no examples right now at the moment. So I can have, for example, 2, 2. That's a pair of real numbers. So it's an element of the set R cross R. Now, in general, so when I use capital letters, I frequently use them for sets. In general, if A and B are sets, I have A cross B, and this is the set of pairs. With first component in A, and second component in B. Again, I haven't done anything substantial. I'm just describing language. So for example, I could consider Q cross N. These are two sets. And then I have something like, well, what's a rational number? 1/2 is a rational number, and then 2 is a natural number. So this is a pair where the first number is a rational number and the second number is a natural number. So this is just a piece of notation, right? Nothing substantial here, nothing deep. Just language. Okay, the next thing is if X is in A implies that X is in B for all X. In other words, if every element of A is an element of B, then we write A is a subset of B and say A is a subset of B. So to give an example, all natural numbers are integers. All integers are rational numbers. All rational numbers are real numbers. And none of these containments reverse, right? So we have this bigger sets in the sense of being a superset of the natural numbers, and that's the integers. So there's a nested containment here. So that's a familiar notion, right? Now, for my next definition, we have a notion of subsets. And so there should be a set of all subsets. And that set is denoted by P of, let's script P of A denote the sets of all subsets of A. And I can write this like this, that P of A is the set of all sets B such that B is a subset of A. And I could also use this notation. I forgot to do it in the case of pairs. A cross B can be written as the set of pairs X comma Y such that X is in A and Y is in B. So all of this is language and there's nothing deep here. If you're confused, that's just because I've thrown too many words and too many things. Nothing deep has happened. Does anyone have any questions? Okay. And I'd love that you'd ask questions if you have any. That would be helpful for me. Right. So finally, we get to the notion, I can now answer the following question. What is the relationship between these three things? So let's say we have y is equal to x squared. Then let's say we have f of x is equal to x squared. And we have just the graph of x squared, which looks like a parabola, right? So what is the relationship between these three things? Does anyone have any guesses?
They all mean the same thing.
In a sense, yes, they all describe the same thing, but they describe the same thing in three different lights. What are those three different lights? So that's right, they do describe the same thing, but how do they describe it? So first off, let's say you just have y equals x squared, right? What's the relationship between this expression and this set of points? So for example, let's say I take the point -4, 1. Is the point -4, 1 on the parabola or not?
No,
Why not?
because when you plug it into the equation, the numbers aren't equal.
Exactly. So what are the points that are on the graph?
Those are the ones that would be in f of x.
Yes, they're okay. Sorry, say the full sentence.
The points would be the function of x. I'm not sure how to say it, but
Well, they're the points that satisfy what? Let's say we're comparing it to this one.
satisfy the domain.
Well, this is an equation, right? So you can talk about points that satisfy the equation, right? So let's think about what a graph is. A graph is a collection of points, right? Where do the points live? They live in the plane. So what I'm describing is a set of points in the plane. So first off, a graph in general, okay, let's say this, a relation is a set of points in the plane. And then if I have something like this, an equation, I get the sets of all points x comma y such that y is equal to x squared, right? Now, where does this live? This is an element. So first off, you can say that this is an element of the power sets of R cross R. In other words, it is a subset of points on the plane. You can also say that this is a subset of R cross R. So what is this? This is a set of points in the plane. This is, don't get tangled up in the language. It doesn't matter if you don't understand the language fully. The point is that I've just defined a collection of points in the plane. What are the points in the plane? They're the points in the plane that satisfy the equation, right? So if I have an equation like this, I get a collection of points in the plane, and those are exactly the points in the plane that satisfy the equation. Now, I can write down another equation. I can write down something like x squared plus y squared is equal to 1. And what does the graph of this look like? What are all points satisfying this equation? What does it look like? Oh, there are messages in chats. A circle. Okay, yes, a circle. Yes, so it looks like a circle. So a circle can be described as, the unit circle can be described as all points such that x squared plus y squared is equal to 1, right? So that looks like a circle. Now, the problem is that the circle is not of the form y is equal to something. In other words, I can't write it as a function. So what is a function? Well, we have this idea of the, it is what this is. this is a vertical line, the vertical line test. So in the case of a parabola, every single vertical line has at most one point lying on it. And that means that if I take a point here, I can define the unique point lying above it. And that sort of defines a formula for what the point is above X. In the case of the circle, I can't do this because if I take this point, then there are two different points. So I can't write f of X is equal to something and get the circle. So in general, if I have something and I can essentially solve for y, here I can't solve for y. I can take the square root. I can write y is equal to the square root of 1 minus x squared, but there are two different square roots, and this only gives me the upper half of the circle, not the bottom half of the circle. So this is not the whole circle. And in general, things like this are functions. Things like this are relations. And then these are graphs of relations, or we also call them the relation. If we think of a relation as a subset of points in the plane, then this is the graph. Functions are a special kind of relation, those that satisfy the vertical line test. Okay, so this is, again, more just language. But if you think about it, things of the form f of X equals something, that excludes something like the circle because of this thing that you've heard in high school, the vertical line test, right? So this is just a review of some high school concepts as well. And then in general, the relationship between a graph and a formula is that the graph is exactly the set of points in the plane that satisfy the formula, right? So I can write that here. And then the circle can be described as the set of points x comma y. They're pairs, right? They're ordered pairs, such that x squared plus y squared is equal to 1. Okay, so this took way too long, but this is just a bunch of language. So this is a some set theoretical language. I'm just doing it to give you some exposure because I'm going to be using this language for the remainder of the course. But all of this was just shallow linguistic things. I'm now going to do several slightly harder theoretical things that actually have content. This isn't actually just going to be language. So consider, by the way, does anyone have any questions about anything that we discussed before?
I just have a brief question.
Yeah,
In the yellow parenthesis, I can't really see it that well. What does it say?
Sorry, in the yellow parenthesis?
Yes, it was next to the function of x equals x squared, right to the right of that.
Sorry, yeah, this is supposed to be that. I think you have flux on because that should look green. But yes, with flux, that's a 4. So
Okay.
the point here was that I marked a point on the plane, and that point wasn't a point on the parabola. And I asked why wasn't it a point on the parabola, right?
Right. Okay. Thank you so much.
And the answer was because it didn't satisfy the equation. Right. So that's the main point of this example, that the parabola is exactly the set of points satisfying the equation.
I have
Okay.
a question.
Go ahead.
I don't know if someone already asked this, but I wasn't able to jot down some things just because of the pace of it. I didn't know if you already said this or not, but is this going to be like all this notes going to be uploaded?
Yes. So I have a course website, and has anyone not received the email that has the course website? I sent it half an hour before the lecture. You don't have to check now, but so email me if you didn't get it, but in your inbox, you should have a link to the course website, and the course website has these notes uploaded.
Okay.
The notes do not cover the first hour and a half lecture, but that was sort of not inside the scope of calculus. That was the hype lecture.
Okay.
But notes for this are uploaded. I have them printed out here.
Okay, great, thank you.
And then I also recommend in the syllabus, which is also on the website as well as the first homework. In the syllabus, I recommend some books that you can look at. Although I'm going to make my homework be so that you should look at the notes when doing the homework, and then that should guide you. And then the first homework is due before next Tuesday's lecture, so a week from now. Okay. So I'm now going to talk about orderings. So we think of the real numbers, and on the real numbers, we have a notion of less than or equal to. So for example, 1 is less than or equal to 2, and 2 is less than or equal to 4, but it's not the case that 4 is less than or equal to 1. That's not the case, right? So this is an order. Now, formally, we can think of this as a relation. This is more of a tangential remark. Specifically, it is all defined by the sets of all pairs x comma y with x is less than or equal to y. But that's not important. What's important is that we have a notion of less than or equal to, and we're all familiar with this. So, chat question. Oh, the recording can be accessed on Blackboard. So all of the recordings will automatically be uploaded to Blackboard at the end of the lecture. And I'm also going to be posting them on YouTube. Does anyone object to me posting these on YouTube? They're going to be private for now, but I'm probably going to make them public at the end. But the YouTube uploads take a very long time. You can email me privately, by the way, if you have any objections. So private emails are also work. Asking you to object publicly is not fair. Okay, but if you want them quick, you should look at Blackboard after the lecture. And that's an automatic thing. So you should see that the lecture is being recorded to the cloud, and then it'll automatically get posted. Right. Okay, so I'd like to ask, what are some properties of less than or equal to? I have 40 minutes left. So because I have 40 minutes left, I would really prefer to have 2 breaks in subsequent lectures, but today I went slightly over time in the first half. And so I think I'm just going to go and lecture for the next 38 minutes. It's a bit long. Next time I'll have a break earlier on. But I'm going to finish today's lecture on time without a break. No, we should have and insist that we have 2 breaks in subsequent lectures. Anyway, what are some properties? So these properties have names. The names aren't really important. One property is reflexivity. And this says that x is less than or equal to x. Another property is transitivity. And this says that if x is less than or equal to y, and y is less than or equal to x, then, y is less than or equal to z, then x is less than or equal to z. And by the way, I am Canadian and currently located in Canada, so it is z, not z. Okay, another property is anti-symmetry. And this says that if x is less than or equal to y and y is less than or equal to x, then x equals y. So all of these properties should be clear from our usual notion of less than or equal to, right? And then the fourth property, and I'll call this totality, says that for any x comma y, either or both, in case they're equal, x is less than or equal to y, or y is less than or equal to x. But what this says is that any two numbers can be compared. So these four properties define what is called a total order. So in other words, if you have any sets and any relation less than or equal to satisfying those four properties, then it's a total order on it. So some examples of total orders. Whoops. Okay, things are being sad. Some examples of total orders are the less than or equal to on the real numbers. And then we also have an ordering on the natural numbers. We also have an ordering on the rational numbers, and we also have an ordering on the integers, right? So all of these have an order, and the order, the notion of ordering for all of these satisfy these four properties. And you do not have to memorize this. Again, this is just a bit of theory. Well, okay, so here is a really interesting idea. If we drop the fourth condition, we get the notion of a partial order. And I can give you a really good example of a partial order. So a partial order is, again, the definition of a partial order is that it's any ordering relation on any sets that satisfies reflexivity, transitivity, and antisymmetry. So what's an example? Don't worry about the words in the definition. Just think about this example. P of R. So for any set A, P of A, which is the set of subsets of A, has an order given by containments. So for example, if we think of P of R, then we have various sets of real numbers. So we write something like this for the set of numbers between 0 and 1, right? Well, that's a subset of the set of numbers between -1 and 4, right? So in other words, we have an ordering of subsets where bigger sets are bigger. And this is a partial order. It's not a total order because something like 0, 2 and 1, 3 cannot be compared. Because neither is a subset of the other. So this property of totality, which here would say that either A is a subset of B or B is a subset of A, it's false. Because if we picture these as sets on the number line, one set looks like this, and the other set looks like this, right? And neither contains the other. So the containment looks like an ordering relation on sets. It satisfies these three properties. It's sort of clear if you think about it. Each set contains itself. If you're smaller, if A is smaller than B and B is smaller than A, then A is smaller than C. And if two sets contain each other, then they're equal. And I guess that's called in set theory the axiom of extensionality. Again, that's not important. Just what's important is that sets have an order. Now, actually, for this class, we will order P of A by reverse containments. Which means that A is, sorry, I should call these sets B is less than or equal to C, means C is a subset of B. So we want to flip the order around. So we want the bigger sets to be smaller in a sense. Or the C is bigger than B means that C is a subset of B. So if we go up the ordering, our sets become smaller and smaller. And then I'll use this symbol to denote our sets. Now notice that while 0, 2, and 1, 3 cannot be compared, we have that the empty sets is a subset of both. This is the symbol for the empty sets. And so what we have then is that in the ordering, the empty set is bigger than 0, 2, and the empty sets is bigger than 1, 3. So while so the ordering less than or equal to, it's by reverse containment. That's the convention. Let me open this so I get a bit more lights. So what happens is, while not everything can be compared, we can find something above both things that's bigger than both things. And so what we actually have is this fifth property, and this is called directedness for an order, which says that for all xy, there is some z, so that x is less than or equal to z and y is less than or equal to z. So that's true here because the empty set is a subset of both sets, and so the empty set is bigger than any two sets. In fact, there's maximal elements. So if we have a partial order, a directed partial order, we will call it a directed set. So in other words, what is a directed set? A directed set is any set on which we have a notion of less than or equal to, which satisfies the really clear apparent three properties of reflexivity, transitivity, antisymmetry. These are just things that the order should, any order should satisfy. And additionally, you have the property that for any two elements, there's something lying above both of them. And in the case of the order on P of A, that it's a sort of a really boring directed set because there's a maximal elements. There's nothing smaller than the empty set, so the empty set is the biggest thing in this ordering. And it's not really dynamic. So now we get to this most important directed set in all of mathematics. So here is the important definition. Also, I now realize that I'm spending too much time on technical theoretical things. I will spend much more less time on this in the future. I was hoping that this would take much less time. What we're getting to, and this will happen early on in tomorrow's lecture, so I apologize for this, is that I'll just define, using a bunch of abstract machinery, what it means to have an area under the curve and when this is defined. And all of this will come together in there. So remember, our goal with all of this theoretical machinery is just to define the area under the curve. And I've just thrown a bunch of language at you, and all of this language is described in the notes. Okay, so what is the important definition? Well, the important definition is this. If I'm going to define a special ordering on a special collection of sets of real numbers. So if I fix A in R, some real number, so this is the definition that you pay attention to. Then we say that a set of real numbers is a neighborhood of A if, well, so here's the informal definition. If A is in A and A has some wiggle room. So here's the formal definition. If there is some interval x comma y, and here's a really important thing. In math, the notation x comma y refers to two things. So x comma y also refers to, as it's not a pair, it can refer to the set of points the set of points z, so that z is between x and y strictly. So this means two different things. It can either mean the ordered pair, or it can mean all points between x and y, all real numbers between x and y. And the same notation is used for two different things, which is really unfortunate, but you should determine from context. So there is some interval. This is a subset of real numbers, so that A lives inside this interval, and this interval lives in as a subset of A. So in other words, let's look at it like this. Here's a picture. Suppose this is my A. So imagine that this is a set of real numbers. So this is my number line. And then I consider something like this. So this straight line means that I'm including this endpoint. This line means that I'm not including this endpoint. Then if I take a point here, then this point lives inside the blue set. And moreover, it has some wiggle room, right? It has an interval of points around it living inside of here. So this, so the blue set is, let's say the blue set is A. A is a neighborhood of this point. But A is not a neighborhood of this point. Because this point has no wiggle room. Any questions? So sorry, this is too theoretical. I will tone down the theory next class. I realized that I was calibrated. This is too formal. Okay, so so we have this idea of neighborhoods, and then I will denote the set of all neighborhoods of A by OA, script OA. So this is a script O. This letter is a script O. So this is the set of neighborhoods of A. So in other words, if I have a number line and I choose some point on the number line, then I can consider the sets, not of all subsets of real numbers, but the set of sets that contain A and have some wiggle room for A to move around in. And this, so OA is ordered by reverse inclusion. Just like the set of all subsets of real numbers. But now look at this. Look at this. Suppose A and B are neighborhoods of A. This means that A lives inside some interval, let's say x1, y1, that lives inside of A, and that A, this is the wiggle room, has some wiggle room inside of B. Then in general, so by the way, what does this mean? This right here means that x1 is less than A is less than y1. These are intervals, not ordered pairs. Then if we look at this, the maximum of x1 and x2, x1 is less than A and x2 is less than A. This is going to also be less than A, and A is going to be less than the minimum of y1 and y2. So in other words, A is going to be a point in the interval max x1, x2 with other endpoint minimum y1 and y2. And this is going to live inside both A and B. And I use the intersection so the intersection of two sets is the set of all points that lie inside of both sets. So this is the intersection.
I'm sorry, could you repeat the definition for an intersection?
Yes, good, thanks. So A intersect B is the set of points X such that X is in A and X is in B. So I'll give you a few examples. Let's say you take all points between 0 and 2, and you take all points between 1 and 3. Then which points lie both between 0 and 2 and between 1 and 3?
1 and 2.
Right, the interval of points between 1 and 2, right? So exactly when a point is between 1 and 2, inclusive of the endpoints, will it be in satisfy both of these conditions? So to draw this on the number line, again, always go back to the number line. One interval looks like this, the other interval looks like this. And their intersection looks like this, right? So that's what an intersection looks like. So what I've done then is I've shown, if I look at this equation right here, well, this sentence. This shows that A intersect B is a neighborhood of A. In other words, A intersect B is an element of the set of neighborhoods of A. So we started off with two neighborhoods of A. Remember that a neighborhood of A is some set that has A and that A has some wiggle room inside. And so was supposing that both of these were neighborhoods of A meant that A was inside both sets and they had some wiggle room. Now, what I've done is I've taken both of these wiggle rooms and I've shrunk it down to their intersection. But their intersection looks like this, and this is still their intersection contains this interval. So I've shown here that the intersection of two sets that have wiggle room around A have wiggle room around A. So if you take anything from this, it's that sentence. The intersection of two sets that have wiggle room around A have wiggle room around A. And so that shows this. And so, and notice that A intersect B is a subset of A, and A intersect B is a subset of B, just by definition, because it's a set of all points that lie in both A and B. So the points in A and B lie in A, and the points in A and B lie in B. Now, by my ordering, this means that, by the way, what time is it? 14 minutes left. That A is less than or equal to A intersect B, and that B is less than or equal to A intersect B. So OA, so is a directed set. In other words, if I take two neighborhoods of a point, I can form their intersection. And if with respect to reverse inclusion, it's bigger than either of the sets. So for any two sets, I can find some set living above it. Now, here's the, before when we considered just all sets of real numbers, it was directed for a very silly reason. It was directed because the empty set was inside all of them. So the empty set was this maximal element. But here we have a much more dynamic order. It's a much more lively order. The problem is that you can't eliminate all of the wiggle room around A. There's no maximal elements. If you have two neighborhoods of A, then you can always find some smaller amount of wiggle room. But you can't eliminate all of the wiggle room. So this is a much more interesting directed set. Okay, so I promise that next lecture, I will make this much less theoretical. This has been too abstract. I did not realize that this would come off as abstract as it did. Oh, that is, I pressed on pause. Whoops, there we are. So that covers the first 3 pages of my notes. Okay, I'm going to define one more concept today. So now I'm going to get to the limits. So all of this directed set machinery, if you just remember one thing about it, and again, you're not supposed to memorize all of this, you're not even supposed to understand all of this. Just try and we're going to get to examples next time, but next time is also still going to be theoretical. Next week, we are going to literally just be doing calculations. But I'd like to establish some foundations for this. So in a sense, I showed you what the Greeks have done, and then in the modern sense, in order to make everything precise, you have to talk about this. So it's just some stuff that I'm going to put out there, but it's not examinable. If you think about it, it's going to make a bunch of notions next time more clear, and it's going to be helpful for understanding calculus. Okay, so let's talk about limits for a bit. So there are 2 notions of limits. In calculus 1, in calc A, you saw the expression limits as x goes to a of f of x, right? So you have some experience with limits like this. There's another notion in calc C. We will use a lot more the notion of the limits as n goes to infinity. Or I actually here, I won't write as n goes to infinity. I'll just write n, the limit of as n. Okay, maybe I will write n goes to infinity of some sequence of points. The limit of a sequence. And I'm going to discuss this here because A, you're going to use it in calc C, and B, because it's actually an easier concept than the limit of a function, and it unifies the notion, all these notions of limits. And as we're going to see, the integral is also going to be defined as a limit that in a very way that's very similar to both of these. So first off, I will discuss this notion first. We'll discuss this first. So a sequence is for every natural number some real number. So in other words, I can consider the sequence, for example, of 1, 1/2, 1/3, 1/4, 1/5, and so on. Now, what do I mean by this? By this, I mean that for every n, natural number n, now not n contains 0, so I have to be careful. Let's x sub n equal to 1 over n plus 1. So when x is 0, this is 1. When x is 0, this is 1/2, then 1/3, then 1/4, then 1/5, right? So for every natural number, I've defined a real number. Well, we say it should be the case if we just look at this. Let's suppose that here I'm just going to put all of the natural numbers. So let's say I have 1 here, I have 2 here, I have 3 here. Let's put them closer. And let's say that's this point right here is 1. So at 1, I have the point 1, then I have a half, then I have a third, then I have a quarter. My third should be a bit higher. Then I have a fifth, then I have a sixth. And these get smaller, right? So as n tends to infinity, now I don't want to keep writing the 1 over n plus 1. That's a bit annoying. I'll just write 1 over n. 1 over n gets small. So we should have that the limits as the natural number n goes to infinity of 1 over n is equal to 0, right? That sounds reasonable. As n gets very big, these expressions 1 over n become very small, and eventually they should converge to 0. Now, what does that mean? So I will make this precise. And in these 5 minutes, I'll just define the notion. And then next time, I promise that I will be less theoretical. So I was too theoretical today. That was miscalibrated. I will admit that. So why? Why is the limit of 1 over n equal to 0? So does anyone have actually? Let's ask. Does anyone have any good arguments for it? Informal. Why should 1 over n go to 0? I mean, you can rephrase what I said. Anyone?
The part where you said as n gets bigger, 1 over n gets smaller.
Right. And you can say eventually gets as small as we want, right? So, well, yeah, that's a good answer. Why? Because as 1 over, as n gets big. Okay, I guess I wrote that here. Big. 1 over n is, I'll write eventually arbitrarily small. And so there are 2 really loaded expressions in this sentence. One is the word eventually, and the other is the expression arbitrarily small. And so in general, here's going to be the idea. Here is going to be the lesson of why I talked about orderings. The word in all notions of limits in mathematics whatsoever, any type of limits, the word eventually refers to a directed sets. And the word arbitrarily small, or I'll just write, or the word arbitrarily is parameterized by the neighborhoods of a point. So what does eventually mean? Eventually, in the case, so remember that the natural numbers have an order, n has an order. So eventually means that some condition holds eventually. in the sense that there is some n I'll write capital N, so that the condition is met. When n is greater than or equal to capital N. And I'll be very precise about this in a second. Let me add a bit more space. Now, okay, here we are, arbitrarily small. Close to 0 means that x sub n is eventually in any neighborhood of 0. Now, why is this? Because we want to talk about limits. The sequence doesn't have to exactly be 0 at any point for it to converge. It just has to get close to 0. And so if we want to parameterize closeness, then we should talk about some wiggle room. So close admits wiggle room. So neighborhoods are appropriate. Okay, I will now give the definition and I will explain the definition next time. A sequence, we say x sub n converges to L, where L is some number. If for all neighborhoods A of L, we have some n, a natural number, so that's x little n is in this neighborhood whenever n is greater than or equal to n. So I'll say a bit more about this next time, and I should end now. The main idea is that arbitrarily close is really parameterized by having some wiggle room. But we say no matter how little wiggle room you give, the sequence eventually has to fit within that wiggle room. And what does eventually mean? It means that there's some point so that it's eventually within that wiggle room after that point. And so this definition just unwraps that. Okay, so that finishes the lecture for today. I'll say one more thing. I'll show you the homework. So the homework, I think I made the homework too hard. Let me pull it up quickly. This is the homework. So there are several problems on the homework. In particular, the problem 1, the problem 2, and the problem 8, which is a bonus problem. That do not use anything that's just use material from before. So you should start attempting problems 1, 2, and 8. Then problem number 3 is a bit unfair, and I'll discuss why next time. Problem 4 uses problem 3, the solution. Although I haven't done any examples of limits yet. So you can consider that you're not able to work on 3 and 4 now. But right now you can start working on problems 1, 2, and 8, and you can consult the notes and read ahead. Remember that I expect each one of problems 1 and 2 to take you longer than an hour each. These are meant to be hard problems, and they'll get easier on the next assignments.